All right, AP Chem. This is going to be your last video lecture for Chapter 6. This is a combination of Section 5 and 6. We'll talk about present and future sources of energy. So what we've been talking about so far this chapter is essentially how the world works. Okay, how you used your car to get to school today, or how you use your stove to cook the food that you've eaten so far today. How we can generate energy. And remember, energy is a capacity to do work. So if we want to accomplish something, do work, we have to have some amount of energy. How do we generate that energy? Certain chemical reactions that provide an excess of energy. Now, what our world uses right now is a combination of fossil fuels. Really, fossil fuels are the main source of energy that we have. We have petroleum-based fossil fuels, things like gas and oil. We have natural gases, things like methane gas, and then we have coal, okay, which really is a fossil fuel. It's a very heavy carbon source, and a lot of people still use wood. My parents in their house, they have a wood stove, and so if they want to be warm, they burn wood. There is hydroelectric power, most commonly generated in hydroelectric dams, okay, as water actualizes its potential energy, becomes kinetic energy. It falls, through a gradient, and it has force. Okay, it's accelerated by gravity. It has a force, and as it passes through a dam or some sort of opening, it turns some sort of paddle, and that movement is captured and creates electric power, and that's one of the ways that we produce energy. And there's also nuclear energy, which is a little bit more confusing. It's not really going to be something we cover in depth in this class because it's not greatly covered in the AP exam. All right, this is a chart that shows major energy sources in the United States, not worldwide, but just in the United States, at different points in time. We have starting at 1850, ending in the year 2000. So as you can tell, and understandably so, in 1850, most of the energy that was produced in the United States was from wood, the combustion of wood, and the remainder was from the combustion of coal. Moving forward 50 years, huge decrease in the amount of wood that was used to be burned, and that was replaced with coal. And you can see, starting as early as the year 1900, there's a small amount of petroleum, gasoline, and natural gas usage, as well as hydro and nuclear power. And no, it wasn't nuclear power in the year 1900, but that was the beginning of hydroelectric energy. The dams that were created around that time were the first source of hydroelectric power that we had. Moving forward into 1950, again, there was yet another decrease in the amount of wood that was used, a huge spike in petroleum and natural gas, and a very, very small increase in the amount of hydroelectric power and nuclear power. Moving forward, as you can see, in 1975, as well as in the present day, the petroleum natural gas is the major and preferred source of energy within the United States. However, I would like to point out that there is a strong spike. It's a relative spike. It's a near doubling in the amount of hydroelectric and nuclear power in simply 25 years. In this instance, it's going to be a huge increase in the amount of nuclear power. And nuclear power is a huge well of potential energy that we are learning how to tap. The issue is not getting that energy out. The issue is getting that energy out safely. Okay, this is a lot of energy being generated from not a lot of material, and it's very, very hard to contain. Very, very extreme situations are required in order to contain the products that are used, the reactions that are used in nuclear power. And any issue that you've ever heard about nuclear power probably stems from the safety issue, not from the amount of power that we're able to extract from it or the cost of nuclear power. Nuclear power is actually very, very energy efficient and cost efficient. It's the safety there. So one of the huge issues that you've heard is the Earth undergoing a accelerated greenhouse effect. Just as a quick a reminder what that greenhouse effect is. It has to do with the Earth's atmosphere, and the Earth's atmosphere is transparent to visible light from the sun. So high energy light is able to move right through the Earth's atmosphere with no issue. Now, but when that visible light strikes the Earth's surface, okay, the solid Earth, it is changed. It leaves off some of its energy in that solid Earth, warms the Earth itself, and the remainder is irradiated off, but it's in a lower energy form. Again, it deposited some of its energy on the Earth's surface, and it's now a lower energy version of light that's called infrared radiation. Now, whereas visible light can move straight through the Earth's atmosphere and not be absorbed by anything, infrared radiation can most certainly be absorbed by lots of things. It's strongly absorbed by carbon dioxide and water. And there are several other molecules, substances in the Earth's atmosphere that occur at small amounts that very strongly absorb that heat. And so when you look at the composition of the Earth's atmosphere, mostly nitrogen, around 20% oxygen, the part that is warming the Earth really only takes up somewhere, depending on who you listen to, somewhere between 2 to 5% of the Earth's atmosphere, because those particles, those molecules strongly absorb that. And so what's happening is those gases, those substances that are in the Earth's atmosphere are trapping that heat. They're absorbing it, not allowing it to continue off into space where it's not going to affect us. It keeps that heat in the atmosphere. And as a result, the Earth's atmosphere is warmer than it would normally be. And that's not always a bad thing. Okay, without CO2 and without water vapor in our atmosphere, there would be no life on Earth. Okay, not because it would be too cold, but because the swing in temperatures would be too great. Take, for example, Mercury, the first planet from the sun. Mercury doesn't experience the highest temperatures in our solar system. Venus actually does that. But what Mercury does have is the greatest swing from daytime high, meaning the part of Mercury that's facing the sun, a daytime high, and nighttime low, nighttime being the side of Mercury that's not facing the sun. It has the biggest swing between daytime high and nighttime low out of any planet in the solar system. And the reason being because during nighttime, the nighttime, there's no atmosphere on Mercury to trap that warmth. Okay, if there was no atmosphere trapping warmth on Earth, we would get down to, around minus 200 degrees Celsius. And that's not something that our bodies are designed to withstand. So here's a diagram depicting that. We have visible light from the sun, always depicted as parallel lines because it's from a great distance, impacting the Earth. And we have infrared light radiated away by the Earth. It's flying into space. But the presence of CO2 and water molecules in the Earth's atmosphere here in this kind of shaded blue area, they trap that infrared radiation. So moving forward, we have an issue today with the amount of carbon dioxide, carbon monoxide, and other molecules in our atmosphere trapping energy. And that might not seem like too big of a deal. So what if it gets a couple degrees hotter? As it's important to understand that if the average temperature of ocean water were to increase by 6 degrees Celsius, essentially life as we know it would come to an end. Just 6 degrees. 6 degrees Celsius doesn't seem like that big of a deal, but like we've covered already in this chapter, the specific heat of water is very, very high, meaning if you're going to raise the temperature of water, it takes a relatively large amount of energy. So if we were to raise the average temperature of ocean water from its measured temperature, I believe it was in 1980, 6 degrees Celsius, that would be an addition of enough energy into the Earth system that weather systems would become unstable, and through a huge chain reaction of cataclysmic events, life as we know it would end. It wouldn't be hard times. It wouldn't be, we'd all have to go on diets and share our resources. Life as we know it would come to an end. And so it's a very real issue The average ocean temperature has already gone up about 2 degrees Celsius, so we're not that far away. We're not that far away from this big, huge catastrophe. So looking forward, how can we utilize energy? How can we generate energy to do the work that we need to do without generating more carbon dioxide, more carbon monoxide, and other greenhouse gases? Well, people say, like, we can't use coal anymore. That's not exactly true. One of the processes that's been shown to have some promise is something called coal conversion. Now, we don't want to combust coal, and we don't want to combust coal for heat, but what we can do is we can change coal. We can treat coal with steam, and let's see, I believe it was oxygen. Okay, we can treat it with oxygen and steam, and we can actually change coal into methane, CO2, and CO, carbon monoxide. And when we do that, the enthalpies of formation of those are such that we have access to more energy than we would if we simply burned the coal. So if we can convert this coal into what some people call synth gas, or synthetic gas, or synth gas, we have access to that. We have access to methane, which is a not perfectly clean, but it's a much cleaner form of energy. Hydrogen as a fuel. Anyone who has ever watched the old video of the Hindenburg going down, you understand how much energy is available in hydrogen. It's very reactive, reacts very easily, and it's fairly abundant. There are cars that are fueled by hydrogen on the road. They're just not cost efficient to make. Okay, the hydrogen itself is not expensive to acquire. There isn't really an infrastructure to deliver the hydrogen on a regular basis, but the hydrogen itself is not expensive. So that is a very real option. However, it's going to require some sort of change in the infrastructure for the delivery of fuels and the delivery of automobiles themselves. Other things that you might have heard of: oil shale. Okay, extracting hydrocarbons from oil shale as well as seed oils will always generate some amount of a carbon molecule that can be used in the same way that coal can. And then I'm sure that you've seen on certain gas pumps, 10% ethanol, or maybe you've even seen a methanol gas pump. But alcohols, okay, methanol and ethanol are both alcohols, but those are hydrocarbons. And the combustion of those hydrocarbons release energy in the same way that any other fuel does. However, they can be combusted in such a way that we can contain the output to be liquid water, and we can reuse those gases. We can have a closed system and not simply pump those reactants into the air where they can cause some sort of cumulative damage. All right, guys, that is the end of Chapter 6. Please be sure to complete the associated worksheets for these sections 5 and 6. I know this particular video lecture and this particular worksheet aren't very long. Please don't wait to the last second to do it. It's worth your time. If you have any issues with one of the problems, be sure to mark that problem and come to class with a question ready to ask. All right, I will see you next period.